Hello and welcome again to this series of videos where we continue to talk about momentum, and we have just talked about this equation here, a very important equation. F is equal to ma, and we said this is the resultant force acting on the object, and that resultant force produces or causes an acceleration a on the object. It is the same equation which stems from the definition of force, because force is defined as the rate of change of momentum. Now, I'd like us to consider a situation here. Suppose we have this object here. It may be a curve 1,500 kilograms. Let's say the driving force of the engine exerts a force of 7,500 newtons on the car for a time of 10 seconds against an air resistance of, let's say, 2,000 newtons, something like that. So there are two forces acting on that object. And in most cases, remember, the forces acting on an object are more than two. Even in situations where the object appears to be stationary, the forces acting are more than two. For example, right now, I'm standing on this floor and it appears as if no force is acting on me, but there are basically two forces which are acting on me. Number one, the earth is pulling me downwards. If the floor was not there, I would sink downwards. The second force is the floor is exerting a force on me upwards. So those are two forces acting on me, one downwards, the other one upwards. But because their magnitudes are equal, they cancel out each other and they keep me in equilibrium. So I'm in equilibrium because the two forces acting on me are equal in magnitude and opposite in direction. Similarly, on this car, there is a resistance on the bodywork of the car, and there is the driving force. That means that the resultant force acting on that car is this minus this, which is 5,500 newtons in that direction. So that resultant force of 5,500 newtons produces an acceleration A on the car. You can work out that acceleration and you'll find that the car accelerates to the right. It accelerates to the right. What is the direction of the resultant force? To the right. What is the direction of the acceleration? Again, to the right. So this car will accelerate to the right like that. So understand, when you're using this equation, the force you use here is not this one, it's not this one, it is a combination of the two, or any other number of forces acting on the object. I've taught you how to work out the resultant force acting in a given situation, even if they are not parallel to each other. I've taught you that. And if you've not watched that video, make a point of watching that video because it has everything that we are talking about here. And notice that I keep on talking about resultant force. Resultant force is the one force which combines, which is the sum of all the forces acting on that particular object. Now, if this force is acting on this object for 10 seconds, let's break down this equation. F is equal to ma and see what it gives us. This is change in velocity divided by time. If I multiply both sides by t, I'm going to get F times t is going to be equal to m delta v, like that. What I have on the right hand side is change in momentum. What I have on the right hand side is change in momentum. What I have on the left hand side is force times time. So if I multiply this resultant force of 5,500 times 10 seconds, I'm going to get the change in momentum. 55,000 Newton seconds. Now, let me explain something here. When I defined momentum, I said that the units of momentum are kilograms meter per second or Newton seconds. Now is the time to see how the Newton seconds come about. On the right hand side, I have kilograms meter per second because it is change in momentum, and change in momentum has got the units kilograms meter per second. What do I have on the left? Newton seconds. Like that. So this is the time that you should be able to understand how the units for kilograms meter per second became equal to Newton seconds. Very important. So something else that stems from this, the product of the force and the time is referred to as impulse. Impulse. So we have already seen this. This is force times time is going to be equal to change in momentum. What I have on the left hand side, the product of the force and the time, is referred to as impulse. Of course, what I have on the right hand side is change in momentum. This is referred to as the impulse, as momentum impulse relationship or principle. What is impulse? When we talk about a certain amount of resultant force acting for a certain duration of time, the product of that force and the force for which and the time for which it is acting is what we refer to as impulse, and its units are Newton seconds. So the product of force and momentum, force and time, is impulse. That is how it is defined. So in this video, we've been able to clarify when to use F is equals to ma. What F represents, it is the resultant force acting on that object of mass m. It ends up producing an acceleration a on the object. And then we broke down the equation and we are able to see that impulse equals to change in momentum. We can continue to break down that equation and we will be able to see other situations. But we are going to look at this in the next video, where we continue looking at the applications of F is equals to ma, especially in problem solving. So see you in the next lecture.